Okay, so this is last week I talked a little bit about 2 weeks ago. Talked a little bit about some material from Paul Cohen's book. Today I'm going to finish off material from that. This is some lessons for evaluators of DARPA program is the way he pitched it because he was actually a consultant for DARPA. I'm actually going to look at it some lessons for evaluation of programs, but the two are clearly related. If you think about how a large government funding agency has been told to think about evaluating programs, might affect how you evaluate your own program. So some general lessons about how to conduct evaluation of large-scale DARPA programs. And think of this as how do I do large-scale evaluation of programs in general or things that are going to be large. Now, there's a few differences because some of this is based on something that every DARPA program manager should know, so everyone should know about program evaluation with a case study from a particular program in the IPTO office. And some checklists for evaluation designs. So, and I'm trying to stick to what he said because one, it's in his material, so you can always use his book as a reference, but also so you can sort of look at this at a much broader point of view. Thinking about how people who someday might fund your research or might have funded the research you're working on might be looking at evaluation, might change how you want to look at how you do your own work of evaluation, because these are some of the metrics they'll be thinking of. Even if they never mention Paul Cohen, this material has been passed down from program officer to program officer. This was in the late 90s, but one of my colleagues who currently works there said some of this stuff is still stuff talked about today. So program officers at a research agency like DARPA have three masters: the director, the program manager, and the researchers. So the director is the boss's boss, the manager of this program, right, from where you're looking at, right? This is the person who's doing the program management, and then the researchers. So I have to do evaluation that makes the researchers comply, get done what we want. I have to make a case to my boss, and then of course I have to manage my life. So those three different things drive program evaluations in very different ways. A well-designed evaluation will give stakeholders, these three stakeholders, what they need, but if a compromise is necessary, the evaluator has to broker what it's going to be. Sometimes the program participants may not be happy with it. Sometimes his boss may or may not be happy with it, but he or she's got to find a way to make that work. The evaluator is not there to trip up performers. The goal of no program manager is to have their program fail. If we trip up, if we trick or somehow make the program, all the program performers look bad, we look bad. So we have to find a balance between making them look good and what's done, right? So our evaluation is designed to test that can be passed. In fact, various program officers have sometimes set the bar low enough that they have to raise the bar because they quickly realize, oh, this was easy. But they don't. But they always set the bar at a reasonable level. And if not, they adjust the bar. Whether it is passed, whether or not you can meet the program performance will be up to what you do as a researcher. Because almost by definition, no DARPA program has answers yet. Right? It's pushing the state of the art. Sometimes they push too far, sometimes they push not far enough, but most of the time they have a pretty good aim of what they're going to try and do. So if you're trying to figure out what the program is going to do as a DARPA program manager, you want to start early. You want to figure out the program claims and protocols really before the BAA is solicited. In practice, what most DARPA program managers do most DARPA program managers do is they go talk with various researchers before they pitch the program. Right? And they talk to those researchers about what should be in the program. What is the state of the art? What can we do? And once they've collected enough information about what really can be done to address this problem, then they go back in and they say, here's exactly what they're going to do. One of the pre-programs that was being discussed last year, I was talking with some program managers, they had a particular goal of what they wanted to do. And after talking to a bunch of researchers, they realized that goal wasn't going to happen. It's so far beyond what we can do now. It might be a goal you can sell, but you need a much narrower piece. And they came back with a much more scaled program, right, where at least in the first 2 years, things are within what we currently think has happened. The last 2 years, they actually put in everything they wanted to see, things that we currently don't believe can happen. But in the first 2 or 3 years, progress will be made, and they may readjust those final goals. I was part of an IARPA program where we did, not just we, everyone who was performers did so well in the first year that they moved our objective for year 2 and made it 10 times harder. They advanced it 10x because we made so much progress in the first year. They're like, well, the problem with clearly we made more progress than we thought, so we're going to advance those goals, right? So they always adjust things. And it wasn't so bad. We exceeded their revised goals by 10x. It's also important for DARPA programs to define their things so that the claims are simple, but that they're actually claims, things you can measure. And it's really good if those measurements are things that sound really impressive, like 10x, right? But really are just like, so if your error is currently at 90%, right? 10x is not necessarily that bad, right? If you're at 99, then don't talk about your error rate. Don't talk about your performance. Going from 99% to 99.9 is not a very, but if I have an error rate of 1% and I make it an error rate of 0.1%, I've got a huge improvement. So part of this is also how you structure your claims. It is recommended that you write the protocol, including the claims, material, subject, methods, right? Write this out, literally as though you were almost writing a paper. Here's the research protocol, here's the data, whatever, not just PowerPoint. This is problematic because when you have a high-level, vague description of what you think the program is going to do, you sometimes miss lots of important details that make the difference between being doable and not being doable. No, it doesn't take much. Even if you write it out, it's easy to miss stuff. But if you try and do it in like 3 or 4 PowerPoint slides, you're almost surely going to miss something. It's a really good idea to run what are called pilot experiments. A number of DARPA programs actually start with what they call seedlings. Seedlings are very small efforts, often to collect data and prove out some ideas before they launch the big BAA, but also to have some data and stuff to go along with it. So, and it's important from a DARPA point of view. Like people say, why are we spending money doing that? We're just going to do a BAA next year. It's like, it's really expensive not to do this. If you don't have preliminary data and you don't have a right scoping, you can spend millions of dollars and not achieve your objectives. So you want to get that out there early. Broad agency announcement. BAA is a funding mechanism by which the government basically says, so BAAs come in, oddly enough, 2 forms. True BAAs are very broad. It's like, do something good, propose whatever you want to us, give us a white paper, based on that we give you back. The other broad agency announcements, which most DARPA ones are, actually have a much more narrow focus. Tell us how you're going to solve this general problem in this area, but it's not scoped so that there's a hard deliverable, like build a physical system. It's like, make research on this, and then we'll have some objectives we will measure you by. It's important, and most DARPA programs do a pretty good job of providing adequate infrastructure for the experiments. If don't be cheap as for the DARPA side, program managers have to recognize, if I'm going to have a $20 million a year program, I should be spending $2 to $4 million a year on infrastructure to support those teams, doing evaluation, providing data sets, providing ground truth, providing evaluation metrics, and maybe even software to run the evaluation on. At a certain level, if I'm giving a bunch of people like $5 million each, I don't want to just trust their results. We can't have them just say, yeah, I did great, right? I got to compare them. So there's normally within the DARPA program something where there's a third-party evaluation or a T&A team that's going to do test and evaluation, or T&E team. So the general lessons from DARPA program evaluation: if you're going to spend tens of millions of the program, require the evaluation to provide more than 1 bit of pass-fail. We'll talk some more about that in lesson 5. Demos are good, explanations better, or as Tony Tether, who was an extremely well-known DARPA program manager for years, passing the test is necessary but not sufficient for continued funding. You actually want to, in most of these DARPA programs, not just have evaluation that lets you make a decision, do these people meet it or not, but which group was better. Because we might have, and it's very common, DARPA programs have a down select. 4 people start in round 1, 3 people survive round 1, go on to round 2, and 1 person goes around to round 3. Right? So as you do that down select, you want to have enough information to make good decisions. You want to be flexible in the design. Multi-year programs that test the same thing each year quickly become ossified. They don't really answer the question. So you want to review and refine claims, metrics, and protocols annually and update them. As I mentioned, right, all the DARPA programs I was in, right, they change their metrics along the way. There's some vague guidelines, but then they adjust them, making them sometimes much more difficult, other times making them a little simpler, and commonly actually changing the direction a little bit. In fact, the face recognition project that I was on for IARPA literally was launched around the cusp of deep learning coming online for face recognition. So in the beginning, that's why the goals were increased by 10x, because we were looking at original face recognition systems when the BAA was written. The first deep recognition face stuff came out around the time we were working on proposals, and all the team said, we're gonna have a part that's face recognition using deep networks, and a part of our proposal is gonna be non-deep face, because we don't know which one will win, because at the time the results really weren't that clear. Within the first year, all of the people were told, no longer do this old-fashioned stuff. Go ahead and just give us your best results, and don't have to worry about doing stuff that is not deep. And it was required in the beginning. That flexibility is important. Let some of the parameters of evaluation, number of subjects, items, be set pragmatically and don't freak about when they change. This is like, so there will be changes. We literally, in the first year, saw our protocol for evaluation change 3 times. Not only did they change the metrics, they changed the protocol, right? So you can't bake in too much what's gonna happen. Part of that depends on how much data you can get, how curated is that data, how labeled is it, and so they scaled what was gonna be happening as they were able to find more data. And avoid this, again, this is ideas for the program officers, right? Avoid methodological purisms. Any fool can say something is not allowed, but your sample size is wrong. A good evaluator finds workarounds and quantifies the confidence. So if you're in a program, you have whatever constraints you have. Find the best arguments and the best analysis for that data that you can afford. Just answering it does or does not work is not sufficient. It's important that you have a claim that you can evaluate, and we'll talk a lot more about that. So something that every DARPA program manager should know, and you should be thinking about whenever you're doing your evaluation. Evaluation begins with claims. Metrics without claims are really meaningless. So if I'm going to measure something, I want to have a claim about what that measurement is telling me. And this is probably the #1 problem that lots of people, in my view, mess up with their evaluation. They measured something, but a claim is about knowing what that something means. What is it telling me about my research problem, my domain, my whatever, right? Not just saying, I measure this number. I can tell you the average temperature of my CPU. That's a metric. Does it have any meaning? Well, if I'm working on cooling systems, it might. If I'm working on algorithms that are supposed to reduce the temperature of my CPU, it might. If I'm working on how fast I can do deep learning, no. Right? So just the fact that I can measure it does not mean meaningful. So the claims are what ties metrics to meaning. The task of experimental science is really to explain variability. Why am I getting different sets of answers? We'll talk a lot more about that today. And anytime I have humans involved, there's always a great source of variability, so I have to deal with those in particular. When I look at things like sample variance, effect size, and sample size, we really want to control the first before ever talking about the last. And if those 3 terms don't make any sense, don't worry, we'll get them today and next week. But I can say I need to have this many subjects, my sample size, to reach some conclusion. But if I can design an experiment that reduces the sample variance, I can get a good conclusion with less data. We'll see how that works out. Demonstrations are good, explanations are better. So demonstrations are something where I show you something and I say, this gives you some idea that our system can achieve its objectives. Explanations are, our system is better because. Something after because is the part you really want to get at in science. Sometimes you can't run big enough experiments to answer that, and you can only just live with demonstrations. Okay? There are lots of people who view DARPA, especially, which is a large agency, they tend to do what some people call demo science. In fact, a lot of their science is geared towards a very large-scale demonstration where there's a big final project. Now, along the way, they might still be focused on doing real evaluation and explanation. But there is a reason for the large-scale demo, which is their funding literally depends on people in Congress and whatever. And so sometimes something that is a tangible, visible result to the end user, DARPA's end user, the military, effectively in Congress, right, where they can see something that shows them progress, even if scientifically it's not a measurement of progress. Grand challenges, any of those kinds of things, right? Something that the people can relate to is an important part of it. So as a scientist, you have to learn to balance. This is what we do for science, and this is what we do to make the people who fund our science work. One of the lessons I learned at one of my first DARPA large program meetings, Craig Fields, who was then the director or deputy director of DARPA, was talking about a large program that we were a part of. And there were lots of people in our community who were very unhappy because this $100 million program was spending 90% of its budget building an autonomous land vehicle that almost all of us looked at and said, this thing is a joke, right? It's not using any of the advanced algorithms. It's just a tank on wheels with a camera, and it pretty just rolls over stuff, right? It wasn't doing any advanced vision, right? And Craig Fields got up and he said, I'm going to start this talk by answering the question that's on most people's minds, which is, why are we spending so much money building this thing that will never see the battlefield, that will never use the advanced algorithms, because it's so far along in this production cycle that if you guys invent something new, we can't fold it into the design, right? That was no. And his view was very simple, and it changed the way I looked at lots of DARPA after that, which is, look, to get $10 million for good science, we had this tax. So what we had to pay to show off the things we did really with the last group of money, but we still got to have those big demos to show it off, right? And it's a platform. And oh, by the way, it will be collecting data that the rest of you will process, but not in real time. Your work won't end up on the platform, but the platform will be a data collection vehicle for a lot of your research, and so you'll deal with it. So, but that view of looking at it is demonstrations are good. In fact, at some level, they're almost necessary, but explanations are really what our job as a scientist were. Came out of that meeting in a very good way for me to understand, right? It's annoying, I have to deal with those, but that's the price you pay to get good science. So almost all explanations from a scientific point of view involve additional factors. In fact, most interesting science is really about interaction effects, not the main effects. The things we can predict really simply are already explained. Science is not looking at those. A lot of what we do, but especially as computer scientists, are about the interaction of multiple different things. How a change in this processor affects the code of my speed. How data affects the way my machine learning algorithm, right? It's not just my machine learning algorithm, it's the data that goes into it, the way it goes in. There's a whole bunch of dimensions where those factors interact. So, and we talked a little bit about this last time, right? Exploratory data analysis, we want to look for explanations in the data. The data has something in it we want to find. And no matter what we want to think about, our theories are partially data-driven. We find that explanation, then we come up with a hypothesis, and we go out and rerun a more formal analysis. Not all studies are experimental, and not all analysis is hypothesis testing, right? Both of these are very important. We want to be doing experimental stuff, we want to do analysis and hypothesis testing, but sometimes core theory is exactly that. It's a theory that says this will happen, and I can have proofs and theorems to go along with it. Experiments help me tie the model to the real world, but once I have that model tied to the real world, I can make conclusions based entirely just on the model, not just because I did a statistical hypothesis test. Statistical significance and meaningful are not the same. Right? There's lots of results which are statistically significant and not at all meaningful. Right? For example, the number of deaths is statistically significantly correlated, the number of deaths from drowning are statistically significantly correlated with the consumption of ice cream. Okay. Is that result meaningful? Okay. Turns out, not really. There's a causal factor called summer weather that affects how often are people swimming and how often are people eating ice cream. It is not that eating ice cream causes drowning. Right? The two aren't that as correlated as people like to think, but they're statistically significant. So we want to be careful to understand the two. So we're going to go through a bunch of those lessons and sort of talk about them in more detail. And this is where it really gets to be more about how it affects your research. So evaluation begins with claims. Most important, immediate, and most neglected part of many evaluation plans. People come up with, here's our plan, here's our data, here's how we're going to analyze it, but they haven't thought about what are the claims and what I'm going to do with it. So what you measure depends on what you know and on what you claim. And one of the reasons this becomes so important is if I don't measure it, I can't evaluate it from a claim. If I don't know what I want to claim, then I don't know what I need to measure, so I might not measure all the right things. So claims are things like X is bigger, faster, stronger, whatever than Y. X varies linearly with Y in the range we care about, some range of data. X and Y agree on most test items. It doesn't matter who used the system, no effect. Did I already do these slides?
This one sounds very familiar.
Yeah, so, but it's something because Paul's book is a little bit brief, so probably already got that one. My algorithm scales better than yours, right? Non-claim, I built it, it runs fine on some test data. So these are all examples of things. This is not a claim, the rest of these are. What your claim is depends on what research you're trying to do, but it's your claim. But you should be precise about what the claim is. Now, this is tricky, because you might be saying, how can I do the claim if I haven't looked at any data yet? I didn't say you didn't look at any data yet, but before I define the evaluation, you're gonna want to have these claims. So you might have done a pilot study, done some empirical data analysis, looked at stuff, and then go back and say, here's the claim. So 2 weeks ago, when we talked about the sort of ring scheduling problem, right? We looked at some data, went back and changed our claims. Nothing wrong with changing your claims, but if you don't have any, then you're not changing them, you're inventing them after the fact. You want to get going on what the claim is. So now let's talk about things that are related to learning, because the example we're going to go through is looking at, as an example, looking at spam detection and mail detection, sort of intrusion detection, related kinds of things. So let's say that we had a claim that the system's performance is due to learned knowledge. So I'm going to say that my system is doing a better job at spam detection because of how it learns. So that's a pretty vague thing, but I'm being pretty precise in making a claim. It's learning because of whatever, right? That's an explanatory statement. It learns because of this. Now, I didn't say anything about the claims, right? Now, what's wrong with that if I just made the claim that way? So there's some positive things about that claim, but what's missing? If I say it learns, its performance improvement is because it has learned knowledge.
Not certain quantifiable type of thing. System performance is 10% better.
So I could have a claim of the amount of performance, that would help, right? But I think there's something more fundamental. What type of learned knowledge? That might help. But this one actually has a classic problem that yes, so I didn't say in comparison to what, right? Its performance improvement is due to learned knowledge. Compared to what? Compared to my algorithm without knowledge, or compared to the state of the art? Right? So there's definitely a problem there. I didn't say what the comparison is. But there's even a more fundamental problem with this one. This is, as I said, I like this one because it's the most common problem I see, probably, or one of the most common, two or three. So, what does performance mean? Right? You all have some definition. So, what did you think I meant by performance? Fast it is, right? There's a whole bunch of dimensions. So when you make a claim, the word performance, right, needs to have a quantifier. Performance as measured how. Right? And if you don't specify what that is, you can get yourself into a whole lot of problems in terms of what you're measuring. Because if I want to measure, for example, how much data is used, then I have to measure very different things. And I want to talk about CPU speed. Or if I want to talk about how memory efficient it is, right? What I measure depends on what I mean by the word performance. Right? So even though it's a claim, that was a very vague claim. Right? Now, if I talk about the learning part of it, right? Come back to that, like, what does learned knowledge mean, right? So what kind of learning system are we talking about, right? Does it have a knowledge base? Predefined knowledge that I structure, that's still learned knowledge, right? The system may or may not learn it on its own. Do I have system that supports integrated learning? So it learns, updates itself, and learns. Is it learning from example or by advice, choosing its own features? There's a ton of learning methods. So that was the second problem. That learned knowledge was not well described. Right? So if I want to have a claim, I have to sort of put those things. So if we go back to our problem, and this is going to actually do a comparison of three reformers, if you will. So I have some subject mails. I'm going to put the subject mails into various folders, and I'm going to have some learning methods. In this case, a knowledge base, an SVM, and I forget what else stood for. What? No, this is much older. This is in the 90s, so really didn't exist. Probably reinforcement learning. So then I have some training data, some test data, and we can talk about, say, classification accuracy. So now we've refined this to, when we're talking about learning, right, we've thrown away a whole bunch of choices of what learning can be, and we've got our performance down to accuracy. Right? We're not looking at speed, we're not looking at memory, we're just looking at accuracy. So if that's what we want to do, we've now reduced our claim that we can make a claim that we have a system whose performance in terms of accuracy is improved by a learning system that uses example data from training to improve its performance on the test data. We still left it pretty vague. There's tons of choices of learning, but at least we're not talking about learning by being told from a knowledge structure. Okay, so if I were to then go through the system and look at this, right, and I look at the accuracy, so these are sort of combining the two lessons, 2 and 3. Empirical task, the empirical science goal is to explain variability. Humans are a large source of variability. So if I looked at different algorithms, and the different algorithms have different colors here, and look at the classification accuracy as I change the number of training instances. Okay, if you'd like to believe that as I gave you more instances, your accuracy would go up, and it sort of heads up a little bit, but these are all over the place. So there's a lot of variation up and down as this system is trying to be evaluated. So can I draw a conclusion about this? Right? It's very difficult to draw which of these is the best algorithm. Right? Or is my algorithm getting better because of learning? Right? So if I look at, say, the green algorithm, right, starts up here and it ends up here, right? Giving it more data didn't actually make it learn. It bounces around so much, right? A couple other algorithms, like the orange ones, started down here and ended up there. But was that just random variation? It's only a small increase, right? None of them has a huge increase. This algorithm is sort of interesting because it goes from here to here to here, and then it just stops. It actually fails if you give it too much data. So that one probably wasn't doing a good job. So we start looking at this from a program or from an evaluation point of view. It brings us to, why do we need statistics? Okay, we need statistics to help understand the variations and whether or not any of the differences are meaningful or they're just caused by random variation. When something obviously works, you often don't think you need statistics. And I've seen plenty of PhD students whose thesis projects have curves, and at the end, they have no statistics. I did a proposal a couple weeks ago with a student. Right? He's like, well, I don't need statistics. Like, what do you mean you don't need statistics, right? And you'd be surprised, sometimes you really don't need statistics, but the only way to know that you don't need statistics is to use statistics. Once you've shown that you don't need statistics, then your next experiment, next variations, you might be able to say they're so similar to this experiment, I don't need them anymore. But most of the time, you really do need to do. Statistics is about the ambiguous cases where things obviously don't work or fail, right? So, but it's also how you look at them. So there are things where you see a nice projected plot, but if I presented the data right, you might see that and miss all the variation. So one of the most common reasons people think they don't need statistics is they just show the average. So if I take this data and I reduce it to just showing you the average of green over this, it's now a point. Now I guarantee if I do the average of green versus the average of orange, green is better than orange on average. But does that mean it's actually meaningful? When you see all the raw data, you see how much they're crossing, right? Here, green, actually green might be better. So here's a few places where orange is better than green, not too many, but there's lots of times when curves end up passing each other. Try it. I'll just finish up one or more slides, then we'll switch over. So when you have a lot of variation and you hide it by reducing the data for presentation, you can think you have a nice clear case. But when things are bouncing around all over the place, you may or may not have that. Until you look at the deeper level and know what's going on, you may or may not be able to answer that. Okay. Ambiguity is generally caused by this variance, and some variance is caused by lack of control. So if you understand what's causing the variance that's making your data go up and down, maybe you can redesign an experiment that reduces it. We actually saw that with the ring scheduling problem, right? Where instead of looking at it, we found a variable that was scaled properly that reduced a bunch of the variance, which allowed us to make a better conclusion. And this is really in the same vein of that. But if you don't get control in your experimental design, you can try and supply it afterwards with statistics, but way better is to design an experiment to reduce the variance so you don't have those problems to begin with. Because fixing it after the fact may or may not be possible. Once I've got a ton of variation, I may not be able to make it go away because if I don't have the raw data to sort of combine all of that. So, we're going to stop this here. We're going to switch over to Riley, who's going to do the presentation, and then we'll come back and finish it. So I know it's a little bit odd to bounce around like that. So, do you have your talk on a stick or?
Yeah.
Yes. So actually, I'm going to, maybe I should stop this.